All right, ladies and gentlemen, welcome back. We are still working our way through chapter 21 in this AP statistics curriculum for statistics modeling our world. We have chapter 21 is kind of like I've said in the last video, a smorgasbord of little things that we address when it comes to hypothesis tests. So in our last video, we talked about alpha values and a little bit more about clarifying what a p-value is. In this video, we are going to spend a little bit of time talking about this word significance and what it means in statistics. And then we are also going to look at the confidence interval and how confidence intervals relate to hypothesis tests. So let's jump into it here, okay? Significance, what do we mean when we say that a test is statistically significant, okay? In the last video, what we said was that statistically significant means that the test statistic had a p-value lower than our alpha level. So being that that's the definition of significance, we have to remember a couple of really important things. First of all, we have to remember that our alpha values are completely arbitrary, right? We choose what the alpha level is, right? We are carrying within our calculations here the threshold of evidence that we are willing to accept. So significance then is entirely based on this arbitrary number that we have chosen for our situation. What I'm trying to say here is that we should not be lulled into thinking that statistically significant means any sense of practical importance. All we're saying when we say something is statistically significant is that the p-value that I calculated is lower than the alpha level that I set for this test. It is statistically significant because I'm willing to accept this level of evidence to reject my null hypothesis. That's it, right? We use the word significance in English to mean lots of different things, right? Like significant meaning that it's important. However, significance has a totally different meaning in statistics. It only means that the test statistic had a p-value lower than our alpha value, okay? For large samples, even small, unimportant, insignificant, quote unquote, deviations from the null hypothesis can still be statistically significant. Remember, when we have a large sample size, that takes our standard error, which is PQ over N. The larger this N number is right here, the smaller the deviations away from the null hypothesis. So if we have a really large sample size, we could find that even the slightest deviation, even if it's very small from the null hypothesis, might still be statistically significant. Again, statistical significance is only as good as the sample and the alpha value that we have set. Okay. On the other hand, if the sample is not large enough, even large financially or scientifically significant differences may not be statistically significant. So to take that same argument, if we were to have a very small sample size, like one maybe that is below what we need for our conditions, the deviations away from the null hypothesis could be quite large and still not be statistically significant. It's all dependent on the situation, okay? This is why when in research and when you're using these statistics to prove something, it's a good practice to report the magnitude of the difference between the observed statistic value and the null hypothesis. That being like our z-score for how far away that would be, okay? We want to do this along with the p-value because if we just say that results are statistically significant and then that's it, we don't say a p-value, then that could mean that my p-value was 0.4 because I personally set my alpha value to 0.5 and that's not good. That's not good research. That's not a good level of evidence. Okay, so we want to make sure that we report those things, right? Reports for statistics should be honest and yet vague in the way that we say something, because a p-value, like we said, the p-value is only a measure of probability. It's the probability in which we would see this sample if the null hypothesis were true. It doesn't say anything about like the actual result. Okay, so that's our little bit about significance there. Questions, comments, concerns, throw them in the comments. Find a way to contact me, and we can work it out there. Let's go to this next little bit, our second bit for today's video. Confidence intervals and hypothesis tests. How do these two things relate, right? And the reality here is that confidence intervals and hypothesis tests are built from the same calculations. They have the same assumptions and conditions. We're using the same normal model to create them, which means that you can approximate a hypothesis test. Now, you can't find a p-value, but you can approximate a hypothesis test by examining a confidence interval. We just ask ourselves whether the null hypothesis value is consistent with the confidence interval for the parameter at the corresponding confidence level. So, for example, just as a quick visual of what we have here, let's just say that from here to here is my confidence interval, right? That's my interval inside there. And let's say that my null hypothesis falls right there. My null hypothesis falls within this interval that I'm saying are plausible values, which means when this happens, we fail to reject. Because if the null hypothesis falls inside the interval, it means that the null hypothesis value is a plausible value. Therefore, we do not have evidence to reject the null hypothesis. We fail to reject. However, if that's my interval and my null hypothesis is over here, it is outside the interval, right? This space, let's make this bigger, because bigger lines make the interval, right? Of course, obviously. If that's my interval and my null hypothesis is outside of that interval, we reject the null hypothesis. Because if the null hypothesis value is outside of the confidence interval, it means that the null hypothesis is not a plausible value. Therefore, our p-value will be below whatever the alpha level is, and then we would reject the null hypothesis. This means that the alpha value that we use to set the threshold for the p-value relates to the confidence interval. So, how does it relate? In general, a confidence interval is, well, confidence intervals are always two-sided. I shouldn't say in general. Confidence intervals are always two-sided. So they correspond to a two-sided test. Remember, on our normal model here, a two-sided test means we're measuring the p-values on both sides. Well, this space in the middle here, that's our confidence interval, right? So a confidence interval relates to a two-sided test. So a confidence level of this percent corresponds to a two-sided hypothesis test with an alpha level of 100 minus whatever that percent is. So let's do a quick example. If my null hypothesis is like p equals 10, and my alternative is p does not equal 10, meaning this is a two-sided test, the alpha level that we choose is related to the confidence level. So, if my confidence level is 95%, that means my alpha level is 100 minus 95. And then these are point numbers, right? Which means that it is 0.05. So an alpha value of 0.05 corresponds to a 95% confidence interval on a two-sided test. Because if this is 95% in the middle, this area on the outside that we measured is 0.05. So the confidence level, it corresponds with the alpha value. And on a two-sided test, it's simply 100 minus whatever your confidence level is. If it's a 99% confidence, then that means we take 100 minus 99, or 0.1, or excuse me, 1.0 minus 0.99. Did I put that in the wrong spot over there? I did. It's supposed to be 1.0. That would be a 0.01 for our alpha value. That's on a two-sided test. On a one-sided test, well, remember, if this in the middle here is our confidence interval, then that means that the alpha is these two things added together. But if it's just, so this is like half alpha, half alpha. So then this side, if it's just a one-sided test, we need to figure out whatever our alpha was before and divide it by 1/2. Or as they stated down here, right? A confidence interval with a confidence level of C% corresponds to a one-sided hypothesis test with an alpha level of 1/2 times 100 minus C. So 95% confidence is going to be a 1/2 times 100 minus 95. So that's 1/2 times 0.05, which is 0.025. So that would be an alpha level of 0.025. If it's a one-sided hypothesis test, and we have a 95% confidence interval, I don't know why I just wrote confident, then the alpha value associated with that is 0.025. Because remember, a two-sided test, it's 95. Those two things together add up 0.05. If I'm just looking at a one side of the test, then I'm just looking at that side only. Right? If this were 90% confidence, then it would be 1/2 times 100 minus 90, which is 1/2 times 10, 0.10, which is 0.05. So on a one-sided test, the 90% confidence level is associated with a 0.05 alpha. Think about your picture of your normal model. So let's do an actual example where we use a confidence interval to approximate a hypothesis test. So here we have another super positive question. Like always, every question in statistics is like teens dying or drinking. So here, look, here's teens dying in a car crash. Teens are at the greatest risk of being killed or injured in traffic crashes. According to the National Highway Traffic Safety Administration, 65% of young people killed were not wearing a safety belt. In 2001, a total of 3,322 teens were killed in motor vehicle crashes, an average of 9 teenagers a day. Because many of these deaths could easily be prevented by the use of seatbelts, several states have begun click it or ticket campaigns in which increased enforcement and publicity have resulted in significantly higher seatbelt use. Overall, use in Massachusetts quickly increased from 51% in 2002 to 64.8% in 2006, with a goal of surpassing the national average of 82%. Recently, a local newspaper reported that a roadblock resulted in 23 tickets to drivers who were unbelted out of 134 stops for inspection. Does this provide evidence that the goal of over 82% compliance was met? Use a confidence interval to test this hypothesis, an alpha level of 0.05. Okay, so a couple things we need to take from this. First of all, we are doing a confidence interval, so we're going to need to, we're using a confidence interval to test the hypothesis. So we are going to use our 4-step hypothesis test process. HAMMOck. Hypothesis, assumptions, conditions, mechanics, conditions. Okay, so I have copied over the pertinent information from the previous page here. And so our goal is to surpass the national average of 82%. And at the most recent sample that we gathered, 23 out of 134 were stopped for inspection. And I should probably add on here that the alpha value that we are supposed to use is 0.10. So let's go through our test here. So first of all, hypothesis. We are looking at so null hypothesis, does the proportion, is it the national average? We're going to assume that the proportion is the national average, and then the alternative hypothesis here is, did we surpass this? Oops, didn't mean to do that. Did we surpass this, which means that are we greater than 0.82? Okay. So there's our hypothesis. Assumptions and conditions. We are using a confidence interval to do it this time. However, remember, the assumptions and conditions are the same. Is there randomness? Randomization. So let's just look at the previous slide for a second. It says, recently a local newspaper reported that a roadblock resulted in 23 tickets to drivers who were unbelted out of 134 stopped. So it doesn't say specifically random. However, is it safe to assume that the roadblock was picking up a random representative sample? And I think that is okay, right? The roadblock would gather a random / representative sample. It does not specifically say those words that it is random, but it is fairly safe to assume that the roadblock would generate a random set, a random sample of drivers. Okay. So randomization, good. What about sample size? Would we have a large enough sample size? Well, 82% is what we're checking, so 0.82 times 134 and 0.82 times, excuse me, not 0.82, 0.18. That's my failure rate times 134. And these two numbers should, just eyeballing it, be big enough. Oops. Trying to work my calculator here and I'm failing at it. Okay, so yeah, that's 110-ish if we round it, and then that would mean that this one's about 24-ish. So both successes and failures are greater than 10. Therefore, the sample size is large enough. And then we should write something along the lines of conditions have been met to create a confidence interval. Or to do, I don't know why I said it that way. That's a strange way to say it. But we can say it either way. To create a confidence interval, or we can say to do a one prop Z interval. So assumptions and conditions are met. We're using an interval, so I'm saying that it's an interval, not a test. And we're ready to go ahead and do the mechanics. So I'm going to go ahead and clear this off, so we have room to do that. Now, mechanics-wise, we are creating a confidence interval. The question is, what is the level of confidence? We need to decide that, because they told us that it is a nuts nut, right? They told us that they want us to use a 0.10 alpha level. So going in reverse now, how do we do the alpha level to the the confidence interval? We need to think. So I like to draw a picture to do this. So what's going to be the percent in here? Well, this is a one-sided test. So if my alpha is 0.10, then that means one side of the test is 0.10, right? This is because they did say our hypothesis was a greater than. So this is a one-sided test. And if my alpha is 0.10, that means one side of this is 0.10. That means that the other side of that is 0.10, which means in the middle we have 80%. So this is an 80% confidence interval that we need to find. And we could go in and find the appropriate z-score to use all of that information. However, I'm going to go ahead and just use my calculator for that. We're going to keep those. And so I'm going to bring this up here, and we'll move it over to the side so we can see the pertinent information. We want to go to stat tests, and we want a one prop z test, which is your A. Our X in this case is the number of people who were wearing a seatbelt. So be careful of the information given. 23 people were ticketed for not wearing a seatbelt, which means we want the number of people that were wearing a seatbelt, which is 134 minus 23. So there's 101, I believe. 111, sorry. 111 that are doing that. And then the sample size is 134. The confidence level is 0.8. And so let's go ahead and calculate that amount. So that is my confidence interval from 0.78 to 0.87. From 0.78 to 0.87. So let's go ahead and throw this in here. Get back into my screen. We had from 0.78 to 0.87, I think is what I said. Old man memory is coming into play here. I'm just going to do it really quick again on my hand calculator that I'm holding so I don't mess this up. Did I just do it wrong again? Yes, I did. This is what happens when you get old. Don't get old. 0.78 to 0.87. Yeah, I was right the first time. Okay, good. And then my p hat here is 0.8283, and my sample size is 134. So that's my interval. We can say we are 80% confident that the proportion of teenagers is between, I said proportion of teenagers who wear their seatbelts. Let's get the context correctly here, otherwise we're losing points on our AP test. Who wear seatbelts? Wear seatbelts in Massachusetts, actually. In MA is between 0.78 and 0.87. Now we need to make a statement about our hypothesis. Our hypothesis, if you recall, was that P is equal to 0.82 and that P is greater than 0.82. So have we reached the point where we are exceeding the national average? And what we can say here, if you look at our interval, does the null hypothesis value rest in the interval? It does, which means we fail to reject the null hypothesis because .82 is in the interval. So we have created the confidence interval to give us information about the hypothesis test. Because 0.82 is inside of the interval that we found, that means that my p-value is going to be large, right? This means a large p-value. Now, we haven't actually calculated the p-value, but I know that it's going to be large just based upon the fact that first of all, our p-hat is very close to p. But because also the p-hat is within the confidence interval, I know that it's going to be larger than the alpha value that we set. So that's it for this video. If you have any questions, comments, concerns, you can leave a comment, try to contact me in some way, and I will definitely do my best to get back to you. Thank you for watching.